Yes, friends, let's come to tutorial 3. In this tutorial, as we discussed, we will be revisiting few concepts, few finer points. One of the observations which I have after seeing the forum questions, that is on stick fixed and stick free static stability. A lot of confusion is there. In fact, a lot of confusions were there when I was taught this concept at my BTech level, so nothing surprising. So I'll try to revisit this so that this confusion is removed for all time. Okay? Please understand one thing. We are very clear about this point that if this is CM versus CL, and I'm flying at this CL, I want to fly another CL2, let's say, then if I want to go to this CL2, the airplane, because it is statically stable, it will generate a negative moment. Why? Because if I want to increase the CL from here, say CL1 to CL2, that means, and keeping the speed, everything same, what does that mean? It means I have to change the angle of attack. Okay? Right? But when I try to also think this way, that at this point the lift equal to weight, and at this point also I want lift equal to weight, and I am not changing the altitude, that means since lift equal to weight and this equal to half rho v square SCL, if I am not changing the altitude, that is rho remaining same, and if I want to fly at a higher CL, if CL is higher, that means to maintain lift equal to weight, I need to fly at a lower speed. Then only it is possible. Right? So if I am balancing lift equal to weight at CL2, where CL2 is more than CL1, that means the velocity, the speed here is less than velocity here. That is the confusion. The next question comes, how do you increase CL? And you know, CL is nothing but CL naught plus CL alpha into alpha. That means if I want to change CL, I have to increase the angle of attack. The moment I try to change CL from CL1 to CL2, this CM versus CL graph tells you that there will be a negative moment implicitly generated because the aircraft is statically stable, but you want to fly at this CL, so you have to deflect the elevator such that this negative moment is neutralized, right? Under that understanding, we try to address the question, what is the delta E required to trim an airplane, at some CL trim. What was the approach? Approach was CM, we write CM equal to CM naught plus CM alpha into alpha plus CM delta E into delta E, and we know CL equal to CL naught plus CL alpha into alpha plus CL delta E into delta E. In the class, we have taken this value to be 0, which is not really 0, but for simplicity, we have taken that for 0. You can always add those expressions. But what we have realized, if I want to fly at a particular CL, and that to be a trim point, that means at that point, this CM should be equal to 0. So what we did, we put CM equal to 0, and this alpha, we said this is the alpha trim, and delta is the delta required. Similarly here, alpha trim and delta required. Right? Now what we did, we solved these two equations, and we derived an expression delta E equal to delta E naught plus d delta E by DCL trim into CL trim. Right. And we also know approximately d delta E by DCL trim is equal to minus DCM by DCL by CM delta E. So with this understanding, it is very clear that if I want to fly at a particular CL, if I know its stability characteristics, if I know its neutral point and CG location. Why I am saying that? Because after all, DCM by DCL is approximately equal to minus of neutral point minus XCG. And this neutral point we talk about is stick fixed. So what is the message? Message is, if you want to fly at a particular CL trim, once you know these values, you know what is the delta E required. And here we use the concept of a stick fixed neutral point. Correct? Why you say stick fixed neutral point? Because we are assuming that although this elevator at any angle of attack, because it is hinged here, it can start floating. We are not allowing that. We are saying that we will not allowing it to float, so fixed. So this tells you, this expression tells you delta E required is, let's say, minus 5 degree. So we say we will take this elevator to minus 5 degree, which is this, and that's all. And the stick is locked. The elevator cannot move up and down. And when I am talking about stick fixed, this also means that when I am starting the reference from where I am going to measure the elevator, in that it is assumed that even at this condition, elevator is not allowed to float. Elevator is here only. From here, so what is the final message? If I want to fly at a particular CL trim, whatever delta E required, as I said, typically let's say minus 5 degree. So we have to, from this reference, we'll push the elevator here and lock it. So here also stick fixed in a sense that we are not giving it permission to float. So whenever you are flying an aircraft, how much elevator required to trim an aircraft for a given CL is decided by this neutral point stick fixed. That is, no floating of the elevator allowed. So that is the number, right? But why there is a need for stick free stability? Please understand, the stick free stability we defined for simple reason that we wanted to model how much stick force pilot will apply to get that elevator, let's say minus 5 degree for this case. So for stick free, concept was used for, one is to develop the stick force requirement to deflect it to desired angle. But how much angle? That is always decided by the stick fixed case. Okay? How much force is required? That, in that analysis, we'll be using stick free concept. This should be very, very clear. Okay? Now, let's see what happens. If you recall, this is the elevator, and let's write elevator. And you know, for a given alpha tail, because there will be pressure distribution over the elevator, and mostly the center pressure of the whole distribution over and below of the elevator will result in the center of pressure being behind the hinge line. This is the hinge line. Normally it's like that. So what will happen at an alpha t? If we leave it free, if we leave it not fixed, then this will give a moment, and by its own nature of the hinge moment characteristics, it will float to an equilibrium, some angle, right? and that will depend upon alpha t. For different alpha t, this angle will go on changing. So let's say if I want to take it to minus 5 degree, and let's say by its inherent nature, it will automatically go to 3 degrees, minus 3 degrees. Then basically pilot has to put effort to take it to another 2 degrees. That is, suppose I require it to take it for 5 degrees, and who decided that 5 degree? Through stick fixed neutral point, say minus 5 degree. Now because of floating tendency, it has gone up to, let's say, minus 3 degrees. So how much effort pilot should put? Pilot should put effort to take it from here to this. But then what happens? The moment it comes here, again, it can have a floating tendency. So pilot has to keep on holding the elevator in normal case, right? And that is why we put trim tab, etc., etc. But the point here is, please understand, when you are talking about stick-free concept, we are assuming that at a given alpha t, the elevator has already floated like this. And that is why CL alpha of the tail reduces. And that is why the neutral point stick-free is ahead of neutral point stick fixed. Because it's floated up at equilibrium, the CL alpha tail has reduced. Okay? That is why neutral point stick free is ahead of neutral point stick fixed. And this condition is taken as a first equilibrium point. From here we take to the next one. For example, let's see. Suppose delta E required is minus 5 degree as given by this relationship where a not stick fixed is used, and that is only to be used, right? But you have seen, suppose because of floating, and if I recall what is floating, we wrote CH equal to CH alpha t into alpha t plus CH delta E into delta E. Remember, CH alpha t means if there is a alpha t tail, there will be a nose down moment because of alpha t. At the same time, there will be restoring moment because of CH delta E. So as it goes up, delta E, so this force comes here, they will try to restore it. So there will be an equilibrium. At equilibrium, their contribution will cancel each other. So CH will become 0. So CH 0, so that will be CH alpha t into alpha t plus CH delta E into delta E, or delta E float equal to minus CH alpha t by CH delta E into alpha t. This we know. So when I am talking about floating tendency, suppose you design CH alpha t and CH delta in such a way that because of floating, this delta E float at that alpha t also becomes minus 5 degree. I repeat this question. Suppose I want delta E minus 5 degree to trim the airplane at given CL trim, and we are clear that this to be evaluated by stick fixed. But what you found, once you allow it to float by itself, it floats up to minus 5 degree. So naturally, if this happens for a particular alpha t, pilot need not apply any force. It will automatically go to minus 5 degree, get trimmed at whatever CL trim is required, right? So the understanding is how much CL trim is required is decided by stick fixed neutral point. That means when we are analyzing the neutral point, we have not allowed the elevator to float, so it is there, fixed, right? So that CL alpha of the tail remains CL alpha tail without any deflection of elevator, okay, at the tail. So this distinction has to be very, very clear. And also, we know stick-free case is valid or really realistic when you are talking about reversible control. That is, if I move the elevator, the stick also moves. If I move the stick, elevator also moves, right? But for modern aircraft, that reversibility is not there. It is now irreversible. So for that, the stick free concept loses its significance as far as finding the stick force is concerned, right? So this should be very, very clear. So a related concept to stick free is trim tab. If we now realize that this is the tail, say this is the elevator, and I have put a trim tab like this. What happens? Suppose you do not put the trim tab here. If I want to fly at -5° elevator, please understand, take a case where the elevator -5° is required, up. So what the pilot will do, pilot will try to pull the stick, in a sense, it will try to reduce the speed and increase the angle of attack so that CL is more and maintains lift equal to weight. But imagine that pilot has to keep on holding the stick. Otherwise, the moment he leaves, because reversible, the elevator will go down. It will not be able to maintain this position. So pilot will get tired. And how this is maintained at -5°? Major contribution is the force applied on the stick. So the stick, there is a moment. So what is done to give a relief to the pilot? You put a trim tab, and the trim tab should deflect like this. And as we are moving like this, you could see that trim tab will generate a force in this direction, and that will give a moment like this, which will keep on holding the elevator at a particular desired angle. And now once the pilot sets that trim tab, then pilot can leave the stick, and we say it's a hands-off flying. Right? That is the beauty of trim tab. And mathematically, what we have shown, CH equal to CH alpha t into alpha t plus CH delta E into delta E plus CH delta t into delta t, where this is the tab deflection, trim tab deflection, right? So when it's hands off, that means this is equal to 0, equal to CH alpha t into alpha t plus CH delta E into delta E plus CH delta t into delta t. So I can easily find out what is the delta t required. That will be minus CH alpha t into alpha t plus CH delta E into delta E divided by CH delta t. So if you design properly for a given alpha t, given delta E, which I need to keep it, I can easily find out how much trim tab deflection is required. So I can easily calibrate this deflection based on this understanding. Okay, final correction will be done by the pilot, right, through a lever. Okay, this is very important as far as flying qualities of an airplane is concerned, right? And when we are talking about stick-free neutral point, we realize that if this is the reference line, I'm measuring from here, if this is N0 bar stick fixed, then N0 bar prime stick free will be ahead of a stick fixed neutral point, right? And if you also recall that when we were talking about how to estimate neutral point stick fixed and neutral point stick free, in that postulation or problem formulation, what we said that for N0 it is that CG location for which effectively d delta E by dCl trim equal to 0. with a little bit of approximation. Although we know neutral point stick fixed is that CG location, exact definition is it is that CG location at which dCm by dCl or dCm by d alpha equal to 0. Okay, so neutral stability. Right? But when you define a stick free neutral point, what did we say? Through the formulation, we said that a naught prime is that CG location at which dFs stick force by dynamic pressure by dCl is equal to 0. Right? So this distinction should be there in your mind. Similar concept we use when you talk about maneuvering point. How do you define maneuvering point for stick fixed? We said it is that CG location at which d delta E by dN equal to 0. And for stick free, we define maneuvering point stick free is that CG location at which dFs by dN equal to 0. Or F is the stick force, N is the load factor. What is N? N is the load factor. Okay? And we have also seen that if this is your N naught stick fixed and this is N naught prime stick free, then Nm is stick fixed maneuvering point will be, if I'm measuring from here, it will be somewhere here, Nm stick fixed maneuvering point. Why? Because we have seen as the airplane goes for a maneuver, just a Q, then there is a QLT by V, this much of angle of attack roughly gets induced, and that gives a force here, and that gives a nose down moment which tries to restore or stabilizing in tendency. Strictly it's a damping in nature. So in our sense we say this aircraft tends to have more stability during maneuver, and that is why the Nm stick fixed maneuvering point is behind stick fixed neutral point. Okay? Then there was questions that this N naught stick fixed, whether I should take power on, should take power off, or propeller windmilling. These questions were there, right? Let us physically understand. You know, if this is the airplane, suppose you estimate neutral point stick fixed, and let's say that point is somewhere here. This is N naught bar. When you compute N naught bar, let's say we have not taken the contribution of engine. Okay, that is this. And we say this is power off. Typically glider without an engine, right? Now suppose the engine is kept somewhere here, nose mounted, let's say IC engine, piston driven engine. Propeller is here. The moment this propeller is here ahead of CG, we know that this at an angle of attack alpha will generate a normal force here as a function of alpha, and that will make this aircraft less stable, right? Because destabilizing in nature. So n naught power on will lie ahead of n naught power off. Clear? That is, this is n naught bar power off, then n naught bar power on will be ahead of n naught power off, because this is more stable case for a nose mounted engine. Now let us see, suppose you are cruising. Let's say you are cruising. When you are cruising, that means you are with a thrust, this is a drag, there is a lift, there is a weight. And let's assume it is a nose mounted engine configuration. Now if I want to calculate delta E, d delta E by dCl is minus static margin by Cm delta E, which is minus n naught bar minus xcg bar by Cm delta E. So if it is cruising, that time, since thrust is on, I should use power on n naught, right? But if it is coming for a landing, okay, approaching for landing, generally what happens during landing, theoretically, these engines should be shut or they are clutched, right? So that although the engine is on, the propeller is not rotating. However, you will see that when it comes down there, because of windmill effect, propeller will start rotating and generate a little bit of thrust. Although you will find it is recommended you keep 20% thrust, but when you say windmilling, theoretically speaking, because of the wind, the propeller is rotating and generating some marginal thrust. So naturally, in this case, I should use how much delta is required for landing and all. I must use n naught corresponding to windmilling. I should not use n naught corresponding to power on, isn't it? And if the engine is off, if windmilling is not there, then I have to use n naught power off for calculation of delta required, right? So that distinction should be there in your mind, okay?